Good afternoon, students. Hope that you are fine. Is my voice audible? Untuk apa akan diulat? Nah. Kadar bang. Bat nangan jenis mana?
Kamu saya ke? Jam.
Bahasa Thai itu bang.
Jam.
Good afternoon. So shall we start the class or wait few minutes more? Is anybody more joining? Can you hear me?
Yes, sir.
Okay. So shall we start the class?
So can you wait for another minute? Like my friend has to join.
Okay, let's wait a minute so that others can join. Okay, so let's start today's class. So yesterday we have just seen about the quantum mechanical model of atom, or what we also call it as the wave mechanical model of atom, or the modern concept of atom. So in that model, I told you that it was actually given by Werner Heisenberg and Erwin Schrödinger. And what they actually told, they told that there isn't any such fixed orbit, but there is orbital. Orbital is actually 3D. So let's see this on the screen. So let me share here the whiteboard. Is this whiteboard visible?
Yes, sir.
Okay, so we have discussed that according to the wave mechanical model of atoms. Okay, let me write it again. That is the wave mechanical model of atom. Wave mechanical model of atom. So this is actually the modern concept of atom. So according to this concept, electron, it can be anywhere outside the nucleus. So for example, if this is the nucleus is positively charged, so electron can be anywhere outside the nucleus. Now this 3D space where the probability of finding an electron is maximum, that's actually called the orbital. So just this is one of the orbital which I have shown it here. So what is actually the orbital? So let's define it. I have already told that we have to talk only in terms of probability, So that means electron can be anywhere outside the nucleus in the 3D space. It can lie on the x-axis, it can lie on the y-axis, it can also lie on the z-axis. So there is probability, it can be anywhere. So that is why we are now not having the orbit, but we are having the orbital. So what is orbital? I have told that it is the 3D space around the nucleus, right? Okay, let me write. It is the 3D space around the nucleus. 3D space around the nucleus, while the probability of, I'll write it, 3D space around the nucleus, where the probability of, where the probability of finding an electron, probability of finding an electron is maximum. So that is called the orbital. So how much maximum? It is 90 to 95%. So that is called the orbital. So it is simply, you have to remember that orbital is the 3D space around the nucleus where the probability of finding an electron, it is maximum 90 to 95%. So that's called the orbital. So orbital, it is always 3D. It is the first thing which you have to remember here. Next is that it actually gives the probability of finding an electron. So you get that whether electron is here. So if electron density is, let's say, here on this side, so that means this orbital is more dense. It has more electron density. So simply, if, for example, let me write, this is the nucleus. Let's say electron density is in this region. So that is the probability of finding an electron. It will be maximum in this lobe here. We will discuss this. This is actually your one of the orbital. It is known as p orbital. So we are having different types of orbitals, and just as this one above orbital, it is having spherical shape. It is known as s orbital. And similarly, we are having this one orbital. This is known as p orbital. So we are having different types of orbitals. So simply any orbital, it is the 3D space around the nucleus where the probability of finding an electron is maximum 90 to 95%. Got it? So now here, this orbital is actually represented mathematically by the wave function that is called psi. As I have already told this in the wave mechanical model of atom, that is actually the Schrodinger's wave equation, isn't it? This psi, it is known as wave function. I have already told you. This is known as wave function. And this wave function, it actually represents the amplitude of the wave. It represents the amplitude of the wave. So actually, this psi, it gives you the probability, psi square. I have told you that psi has no physical significance as such, but psi square has. When we take the square of this psi, what it gives? It gives the probability of finding an electron. So it gives the probability of finding an electron, right? So you have to note down this probability of finding an electron. This psi square, it gives the probability. So for example, let's say I told that electrons in this p orbital, they are just lying in this lobe. So that means in this lobe, the value of psi square, it will be very high. So that is the electron density will be very high. Okay, now let's differentiate between what is the difference between the orbit and the orbital, right? Orbit concept that was given by Neil Bohr, right? But this orbital, it is the modern concept given by combinedly by the Erwin Schrodinger and the Werner Heisenberg. Okay, let's see. Shall I move to the next page? Have you noted down this?
Yes, sir.
Okay. So what is the difference between orbit and orbital? So I will write it here. One is orbit, another is known as orbital. So orbit concept, it was actually given by Bohr. And in this orbit, we have discussed it there that what is orbit? It is just, it is a fixed circular path, right? It is a fixed circular path, correct? I hope you remember in the Bohr's model, it's a fixed circular path. Now, what is the orbital? Orbital, I already told that it is the 3D space around the nucleus, isn't it? 3D space around the nucleus, 3D space around the nucleus, where the probability of finding an electron is maximum. I told 90 to 95%. 5%. So 3D space around the nucleus, where the probability of finding an electron is maximum, where the probability of finding an electron is maximum. So that is called the orbital. So that means you can say that this orbit, it actually represents the planar motion of an electron, right? It represents the planar motion of electron. But this orbital, it represents the 3D, it represents the 3D motion of electron, right? 3-dimensional. That means electron can revolve in all the 3 possible axes, X, Y, and Z. So 3D motion of electron. Okay, then the next difference which you can note down, that all orbits, they are circular, right? All orbits are circular. They are circular, are spherical, but different orbitals have different shapes. You will write here that different orbitals have different shapes. Different orbitals have different shapes. For example, as you have seen in the first slide, that s orbital, it has spherical shape, right? Okay, I will write it here. It's very important. I hope you will note down this, that s orbital has spherical shape. S orbitals have spherical shape, and p orbitals have dumbbell shape. Okay, I will write it here, that p orbital, it has dumbbell shape. It has dumbbell shape. And similarly, d orbitals have double dumbbell shape. d orbital has double dumbbell shape. Double dumbbell shape, right? Double dumbbell shape. And similarly, f orbitals have complex shape. F orbital has complex shape. So you have to note down these. We will discuss in detail ahead the shapes of different orbitals, how this actually spherical shape it looks like, and then how is this dumbbell, then the double dumbbell shape, right? We will discuss it in detail, but here you will just note down that different orbitals have different shapes, but all orbits are circular and they just represent the planar motion, right? Okay, the next difference which you can remember between orbit and orbital, that is, if we are having an orbit, it doesn't it doesn't obey the Heisenberg's uncertainty principle, right? So orbits does not follow Heisenberg's uncertainty principle, right? We have discussed this Heisenberg's uncertainty principle. What it states? It states that it is impossible, right? It is impossible to measure the position and the momentum of an electron with absolute accuracy. So orbits doesn't follow Heisenberg's uncertainty principle, but these orbitals, they obey, right? So you will just note down this, that these do not obey, these do not follow the Heisenberg's uncertainty principle, but these orbitals, they follow the Heisenberg's uncertainty principle. So have you noted down this? Shall I move to the next page?
Yes, sir.
Okay, so let me move to the next. So next difference, I hope you have completed that fourth point, and I wrote that orbits, they do not follow the Heisenberg's uncertainty principle, but these orbitals, they follow, right? Okay, let me write the next one, that is the fifth one. Fifth one is that, and these orbits, they are non-directional. So orbits are non-directional. That means they do not have any direction. They are non-directional. But if we just talk of orbitals, then you can remember that except s orbital, all are directional except s orbital, because s orbital is actually having spherical shape. So all other orbitals are directional. They have direction. They are directional. For example, if I will just give you one of the example. For example, I told that p orbitals have dumbbell shape. It is just like this. There are two lobes. One is this lobe, another is this one. So this is your p orbital. So can you tell me what is the direction of this p orbital? Definitely it has the direction. It is just, if I just call this as the x-axis, so it lies on the x-axis, right? So it has the direction, right? Similarly, let's say this is my y-axis. So if I just draw the orbital like this, so let's say this is the nucleus, this is one of the lobe here, this is the another lobe. So that means this y, and this is the another p orbital. So both are actually these p orbitals, but this p orbital is having direction towards the x-axis and this is having towards the y-axis. So that means except s orbital, you will remember that all other orbitals are directional. All other orbitals are directional, right? They have direction. So have you got this? But orbits are non-directional. Okay, the next difference, that is the very important difference, that is actually how many electrons can be accommodated in an orbit. So you will write that maximum number of electrons that can be accommodated, maximum number of electrons that can be accommodated, maximum number of electrons that can be accommodated in any orbit, is given by 2n square formula. I hope you remember this, right? 2n square. N is the shell number. For example, if I just talk of the key, for the key shell, you remember that n value is 1. So that means 2n square, that is 2 into 1 square. So that will be equal to 2. Then I'm having L, right? So it is your, its n value is 2. So you will write 2 into 2 square. So 2 square is 4, 4 into 2, that's 8. So the maximum electrons that can be accommodated in K, that is 2, and maximum number of electrons that can be accommodated in L shell, so that is 8 electrons. Similarly, you can also calculate in the next M shell, so that is 2 into 3 square. So 3 square, that's 9, 9 twos are 18. So 18 electrons can be accommodated in M shell. Similarly, if you just calculate in N shell, that will be 2 into 4 square. 4 fours are 16 into 2, that is 32 electrons can be accommodated in this fourth shell, right? But can you tell me how many electrons can be accommodated in an orbital? This is just here the orbital, and this one is here orbit, right? Okay, so can you tell me how many electrons can we accommodate in a particular orbital? Can anybody tell me among you? How many electrons can be accommodated? Okay, I will write it here that maximum number of electrons that can be accommodated, maximum number of electrons that can be accommodated in an orbital. So whether it is any orbital, whether it is s orbital or whether it is p orbital, whether it is d orbital, the maximum number of electrons that can be accommodated in an orbital is 2. So that means you can only accommodate 2 electrons in a particular orbital. So whether it is s, whether it is p orbital, whether it is d orbital, whether it is f orbital, any orbital can accommodate only and only 2 electrons, right? So this is the difference between an orbit and orbital. So have you got the difference? Shall we move ahead?
Yes, sir.
Okay, so next we will see the various postulates of this quantum mechanical model, or what we called as wave mechanical model. Okay, let me write it on the next slide. So the postulates of quantum mechanical model, or what you can also call it as wave mechanical model, right? Wave mechanical model. Wave mechanical model. Postulates of wave mechanical model. So postulate number first is that according to this wave mechanical model, which was given by Erwin Schrödinger and Werner Heisenberg, So the first postulate is that the energy of electron is always quantized. You will write this: the energy of electron is always quantized. So that means it has fixed value. It has fixed value. So the energy of electron is always quantized. Quantized means that is having certain definite value, fixed value, having certain fixed value, right? So this is the first postulate of this quantum mechanical model. Next is that now where we get these quantized value of energy, we get it from the solution of Schrodinger's wave equation. So I will write it here. Next postulate is that these quantized values of energy, these quantized values of energy, these quantized values of energy are obtained from solution of Schrodinger wave equation, are obtained from solution of Schrodinger wave equation, right? SWE, it stands for Schrodinger wave equation, right? Schrodinger wave equation. We have discussed that equation yesterday. That is actually del square psi upon del x square plus del square psi upon del y square plus del square psi upon del z square plus 8 pi square m upon h square e minus v psi is equal to 0, right? Okay, then the next postulate is that is actually the Heisenberg's uncertainty principle. What was that? That is, it is impossible. It is impossible. It is impossible to measure. It is impossible to measure the exact position and momentum of an electron. Exact position and momentum of an electron with absolute accuracy. With absolute accuracy, right? So it is impossible to measure the exact position and momentum of an electron with absolute accuracy. That's actually the Heisenberg's uncertainty principle, but this is also one of the postulate of this wave mechanical model, because I have told you that this wave mechanical model, it was collectively given by Erwin Schrödinger as well as the Werner Heisenberg. So this is actually the Heisenberg's uncertainty principle, the third postulate. So have you noted down this? Shall I move to the next slide?
One second.
Okay, sure. Just note down this. So have you completed?
So 1 second.
Sure. You can note down. So shall I move to the next page?
Done, sir.
So the next postulate is regarding the atomic orbital. So I will write it here. That is atomic orbital. It actually describes, okay, write it down, that atomic orbital is described by, it is described by wave function psi, right? It is atomic orbital. It is described by wave function psi, right? That is this. I hope you remember that it's known as psi. P remains silent. But I have already told you that psi has no physical significance as such, but psi square has. So we not only get the one value of this psi, we get different values of psi. So that's why there are different atomic orbitals are possible. So you will write that since psi has different values, since psi has, that is the wave function has different values, therefore different orbitals are possible. Different orbitals are possible. And I have told you that we are having s orbital, right? We are having p orbital. Similarly, we are having d orbital. We are having f orbital. So these are the different types of orbitals. Now, the next very important postulate is that the probability of finding an electron that is actually directly proportional to the value of psi square. Okay, I will write it here. The probability of finding an electron, the probability of finding an electron is directly proportional. It is directly proportional to the value of psi square. So that means more the value of psi square, more will be the probability of finding an electron. So this actually simply gives the electron density, the probability density. So that's why psi square, it is sometimes known as probability density, right? So you can remember that this psi square, it is known as probability density because it actually gives you the probability of finding an electron around the nucleus in the 3D space. So this gives you the probability density. So that means if psi square is having more value, so that means the probability of finding an electron, it will also be more. For example, as we just say that if there are more clouds, then it may definitely rain, right? So there are more possibilities of rain. So similarly, if we are having psi square value is very high, it is more. So that means the probability of finding an electron is also more. Got it? It's very important. So the probability of finding an electron is directly proportional to the value of psi square. So these are the postulates of the wave or the quantum mechanical model of atom. So now, since we are having different types of orbitals and they just have different direction, they are directional and they actually give the probability density. So this psi square is very important. It gives the probability density. Then what we had studied actually, we had studied the quantum numbers. Actually, when we solve this Schrodinger wave equation, we get the three constant values which are known as quantum numbers. So, okay, I will write it here that when Schrodinger wave equation is solved, we get three constants, or you can say the three numbers, right? Known as, which are known as actually the quantum numbers. They are known as quantum numbers. So next topic which we have to study, that is the quantum numbers. So shall I move to the next page?
Yes.
Yeah, sure. Okay. So next is very, very important. So that is your what are quantum numbers. So this will be very important topic for examination point of view. Quantum numbers is asked in the exam. So what are quantum numbers? So see, actually, from the Schrodinger wave equation, we get the three quantum numbers, but actually there are total four quantum numbers. The fourth one was given separately, that we will see here one by one. So you will first write that these quantum numbers, these are set of four numbers. So these are set of four numbers. These are set of four numbers. And what they do, which gives the complete information, which gives the complete information, which gives the complete information, which gives the complete information of an electron. So they give the complete information of an electron in an atom. So like what information? Like the energy of the electron, like the shape of the orbital, like the size of the orbital, like the orientation of the electron, whether electron lies in the x-axis, in the y, or in the z-axis, like the spin of the electron, whether this electron spins in clockwise direction or in the anti-clockwise direction. All this information, it is given by the quantum numbers. And I told you that the first three quantum numbers, they are actually obtained from the solution of Schrodinger wave equation. So now what are these four quantum numbers? The first quantum number is known as principal quantum number. So we are having different quantum numbers. So one is the principal quantum number. So principal quantum number, it is represented by small n. The next one is azimuthal quantum number. Azimuthal quantum number, it is represented by small l. And then the third one is your magnetic quantum number. So magnetic quantum number, it is represented by small m. And these three quantum numbers, that is the principal, azimuthal, and the magnetic, they are actually obtained from the solution of Schrodinger wave equation. I hope you remember the Schrodinger wave equation in short form. What is that? That is actually like this. That is H cap psi is equal to E psi. I hope you remember. This is the short form of Schrodinger wave equation, right? Okay. So then the fourth quantum number was also introduced, that is known as spin quantum number. We are also having spin quantum number, and this spin quantum number, it is represented by small s. So these are the four quantum numbers which actually give the complete information of an electron in an atom, like the shape, size of orbital, like the orientation of electron, like the spin of an electron, whether it will spin in clockwise direction or in the anti-clockwise direction. All this information, it is actually it lies in these four quantum numbers. So let us discuss one by one. So the first one is your principal quantum number. So I told that this principal quantum number, it is represented by n. So what this principal quantum number, who gave this actually? You have to remember that this principal quantum number, it was given by Neil Bohr. So it was given by Neil Bohr. And I hope you remember that n value, it can be 1, it can be 2, isn't it? It can have value 3, 4, 5, etc. Right? And now tell me that if n value is 1, this is your first shell, right? That is your K. And if n value is 2, then it is your L. And similarly, if n value is 3, then it's your M shell. And similarly, if n value is 4, so that's your N shell. Similarly, if n value is 5, so that's your O shell. And similarly, if n is 6, then it will be P. Then after that, it is in the alphabetical order. That is N, O, P, Q, R, etc. So that means you have to remember that this principal quantum number, it gives the information about shells. So it gives information about shells. I will write it here, that it gives information about shells. It gives information about shells. Shell is also known as the main energy level, which we had discussed in the Bohr's model. It's also known as the energy level, or you can simply call it as shell, right? So have you noted down this? Shall I move to the next page?
1 second, sir.
Sure, you can note down.
Down, sir.
Okay, fine. So let's move ahead. So this principal quantum number, it gives the information about shells, right? For example, now can you tell me the order of size of these shells? Order of size. We know that this key, it is having very small size. It is close to the nucleus. Then L is having bigger size, right? And then we are having M, then we are having N. As we have already seen in the Bohr's model, I just told that this, let's say this is the nucleus, this will be the first shell, then this will be the second one, right? This will be the fourth one, this will be the fifth. So let's say this is your key, then it's L, then M and N, etc. So that means as we move away from the nucleus, what happens? The size of these shells, it increases. And now can you tell me what will be the order of energy? Order of energy. Order of energy, which will have very high energy. It is also same, that is K electron which is present in the K, it will have lower energy, then it will be L, then M, then N. So that means energy increases as we move away from the nucleus. Are you getting this? It's very important. I hope you remember the value, you remember the formula. Actually, Neil Bohr gave the formula to calculate the energy of an electron in any shell. That is En is equal to minus 2 pi square, right? M e raised to power 4 z square, right? I hope you remember this. And then it is actually divided by, that is upon n square h square. So I hope you remember this formula. This is the formula to calculate the energy of an electron in any shell, isn't it? Are you getting this? Now, can you tell me here, this is very important. This is very important to know down here, that En is inversely proportional to n square. Is it right? Isn't it? From this formula, what you can write? You can write that energy of an electron in any shell, it is inversely proportional to n square. Here is the n square. You can just see it here. So that means if n value is very high, energy will be low. But what I told, I just told that if we move away from the nucleus, energy increases. Can anybody tell me why? They are just, it seems to be contradictory, but is it like that? No, it is not like that. It's actually having here negative sign. I hope you remember it's minus. So that means if n value is very high, then energy will be low, but it is a negative minus sign here. So that's why you have to remember this order. This is very, very important order. I hope you will remember this order of energy. That is the electron which is present in the key, it will have small energy, lesser energy. Then that electron which is present in the L, and similarly, then that electron which is present in the M, and similarly, then that electron which is present in the N. So have you got this? And you can calculate the energy. I have already given you the formula. That is this one formula, but you can simplify this formula. If you just substitute the values, you get minus 2.18 into 10 to the power minus 18, right? Into z square. Z is the atomic number upon n square. What is n? N is the principal quantum number, or what you can also say it is the shell number, right? And it is in joule per atom. We have already discussed this formula to calculate the energy of electron in any shell, in any energy level. These are also known as energy levels. You can call them as shells or energy levels, but they are 3D, three-dimensional. According to Bohr just told that it is and just 2D. Bohr's model is 2D, planar model, but actually atom is having 3D structure. You have to note down that. So have you noted down this first quantum number? That is actually the principal quantum number, and it gives the information about shells, that is the energy levels. And what we can explain with this principal quantum number? So with this we can explain. So okay, just write like this, that is this quantum number explains man lines of spectra. It explains man lines of spectra. So that means when we just take the spectra of an atom, we get the various lines, the man lines. So those man lines, they can be explained with the help of this quantum number, that is the principal quantum number. So you have to remember that this quantum number, it was given by Neil Bohr, and it just gives the information about the shells, and it's represented by n, and n can have any value, that is 1, 2, 3, 4, right, etc. So got it? Shall I move to the next page?
Yes, sir.
Okay, so then let's see the next very important quantum number, that is known as azimuthal quantum number. So this one is also having other names too. You can remember, one is the azimuthal quantum number. It is also known as angular momentum quantum number, angular momentum quantum number, angular momentum quantum number, or it's also known as subsidiary quantum number. Subsidiary quantum number. So this quantum number, it's represented by small l, and it was given by Sommerfeld. It was given by, so the first quantum number that was actually given by Neil Bohr, and this second quantum number, it is given by Sommerfeld, and this one is represented by L, and L can have values from 0 to n minus 1. 0 to n minus 1. So what is n here? N is the SAM, that is the principal quantum number, which we have already studied. So L can have values from 0 to n minus 1. So just note down this. That is, L can have value from 0 to n minus 1. It's very important. So this azimuthal quantum number, it gives information about subshells. So just note down the first quantum number that actually gives the information about shells, right? Man energy levels, but it gives information about subshells. It gives information about subshells. It gives information about subshells, or you can also call them as sub energy levels. So that means inside the main energy levels, there are also sub energy levels, which is actually your azimuthal quantum number, represented by L. Now this is very important. For example, let's see, so what it actually explains. So I told that the first quantum number that actually explains the main lines of spectra, right? Now this second quantum number, it actually explains. So you'll note down here that this quantum number, it explains fine lines of spectra. As I have told in one of the limitation of Bohr's model was that Bohr's model could explain the main lines of spectra, but could not explain the fine lines of spectra. So these fine lines of spectra, they are explained by this azimuthal quantum number. So it explains fine lines of spectra. Fine lines of spectra. So that means along with the main lines, there are some smaller lines also, which are known as fine lines. So these fine lines of spectra, they are explained by this azimuthal quantum number or angular momentum quantum number. Now let's see, let's take the first shell. What is the first shell? That's your K shell, right? So can you tell me in this K shell, how many subshells will be there? So just calculate this L value. So for K shell, N is equal to 1. So therefore, what will be L value? L will be 0 to n minus 1. So that is 0 to n value is 1 here. So 0 to 1 minus 1. So what is that? That is actually 0 to 0. And what is 0 to 0? That actually means 0. Now here it's very important that 0 doesn't mean nothing. 0 here means one value. So that means there is one subshell. There is one subshell in this key shell. So have you got this? This is very important. You have to remember that in the first key shell, there is one subshell. And what is that one subshell known as? So you will write it that it is known as S subshell. It is known as S subshell. So that means subshells are given the name SPDF. We will see ahead one by one. But first you have to note down this that we are having one subshell in case of the first shell, and that subshell is known as S subshell. And we have just calculated it from this L value. L value is always to be calculated as 0 to n minus 1. So is it clear? Have you noted down this? Shall I move ahead?
Sir, 1 minute, sir.
Sure. Just note down this.
Yes, sir, you can continue.
Okay, sure. So next is the after K shell we are having L shell. So can you tell me in this L shell how many subshells will be there? So what is the n value for this L shell? N value is 2, right? So therefore, can you tell me what will be the L value? L value, I told that it is calculated as 0 to n minus 1, right? So that is 0 to n is here 2, n value is 2, so that is 2 minus 1. So 0 to 2 minus 1, that is what? That is 0 to 1. So 0 to 1 means it has two values, that is 0 and 1. So 0 and 1, it has two values, so that means there are two subshells. Got it? There are two subshells. So can anybody tell me the name of these two subshells? So one is known as S subshell, and another will be known as P subshell. So you have to note down that in case of the first shell, that is K shell, there was only one subshell, that is S subshell. And in case of L shell, there are two subshells. One is the S subshell, another is the P subshell. And how to represent these? You can just represent this S subshell by 2S because N value is here 2. You can just note down this 2 is here and 2 here. Similarly, this 2 P subshell, it will be represented as 2P. Got it? Okay, let me show the previous slide. In the previous one, I told that there is one S subshell. So how will you represent this? You will just represent it by 1S because N value is here 1, right? So 1S means that this is the S subshell of the first shell, that is your K shell, because N value is here 1. Now here, in the second, that is your L shell, N value is 2. So that means S subshell will be represented as 2S and P subshell will be represented as 2P. Okay, then let's move to the next one. That's your M shell. So for M shell, what is the N value? N value is 3, isn't it? N value is 3. So therefore L value will be 0 to n minus 1. I hope you can now calculate yourself, right? So that is 0 to 3 minus 1. So what is 0 to 3 minus 1? So that is 0 to 2. And what is 0 to 2? So that means there is 0, and then there is 1, and then there is 2. So that means there are 3 subshells. There will be 3 subshells in case of M shell. 3 subshells. So can you name these 3 subshells? One will be your S subshell, right? And this will be represented by 3S. Another will be your P subshell. And this P subshell, it will be represented by 3P. And then we are having the D subshell. D subshell, it will be represented by 3D. So are you getting this? This is very, very important concept that you can easily tell how many subshells will be there in any shell. So have you noted down this?
1 minute.
Okay, sure. If anybody has completed this, then just calculate the number of subshells in the N shell. That is the next N shell. Just try yourself.
Sir, you can move to the next slide, sir.
Okay, sure. So let's see then the next shell, that's your N shell. So can you tell me how many subshells will be there in this N shell? Has anybody calculated? So for N shell, small n value is 4. Therefore, L value will be 0 to n minus 1. So that is 0 to n is here 4. That is 0 to 4 minus 1. So that is actually 0 to 3. 4 minus 1, that is 3. So that is here 0, 1, 2, and then 3. So that means there are 4 subshells, correct? There will be 4 subshells. So can you name these 4 subshells? Definitely you can name. That is, first will be S subshell, right? S subshell, and it will be now represented by 4S because it belongs to the 4th shell. That's N value is here 4. Okay, next subshell will be here the P subshell. And this P subshell, it is actually represented by here 4P, correct? Then we are having the D subshell. So this D subshell, it will be here represented by 4D. And similarly, there will be also the F subshell. So this F subshell, it will be represented by 4F, correct? So that means you have to remember that in case of the N shell, that is the 4th shell, there will be 4 subshells. One is the S subshell, P subshell, D subshell, and F subshell. So can anybody tell me where these terms came from? That is S, P, D, and F. S, P, D, and F. These are actually the terms which have just came from spectroscopy, right? These terms have came from spectroscopy. And what is meant by these terms? So actually S, it stands for, S means sharp. S stands for sharp, right? Is my voice audible?
Yes, sir.
Okay, P stands for principal. And then we are having D, it stands for diffused. D stands for diffused. And then we are having the F. F stands for fundamental. F stands for fundamental. Got it? So these, you have to remember that these S, P, D, and F, these terms, they have actually come from spectroscopy, and they actually, what they mean, S stands for sharp, and P stands for principal, D stands for diffused, F stands for fundamental. It's actually when we just take the spectra of any molecule, we get some lines which are sharp. So that's S. We get some lines which are principal line. So that's P. D stands for diffused. Some lines, some spectral lines in the spectra, they are diffused. They are not too much sharp. So similarly, some are the fundamental lines. So these terms you can remember as PDF. It stands for short, principal, diffuser, and fundamental. So now we have seen that in this N shell, there will be how many? There will be 4 subshells. Is it correct? Then if I just tell you that, after N, we are having O shell, right? So can anybody tell me how many subshells will be in their O shell? Can anybody try? So just try it out and tell me the answer. How many subshells will be in the O shell? For O, N value will be 5, right? So what will be the L value? Have you calculated? Can you try it out? It is easy. Just let me know. Shweta, can you tell me what will be the number of subshells here?
For n is equal to 5, sir.
Mhm. Yes, N is equal to 5, and you have to tell me what will be the L value. So what will be the L value? It will be 0 to N minus 1. So that is 0 to 5 minus 1, right? So that is actually
Yes, sir.
0 to 4, and 0 to 4 means how many numbers? 0 to 4 actually means
minus 2.
1,
No, minus
2.
1, 0, 1, and 2.
Where is the minus 1? There isn't any minus 1. We have to start from 0 and we have to end at 4. So it will be 0, 1, 2, 3, and 4. So that means we are having
Yes,
5
sir.
subshells. There will be 5. How many subshells? In this case, there will be 5 subshells, right? 5 subshells. So can you name these
Yes,
5
sir.
subshells? Can you name these 5 subshells? One will be S, another will be P, another will be D, another will be F. What after F? After F, it will be G. That is, you have to go in the alphabetical order. So just if we are having F, and then it will be G, and what will be after G? It will be H, right? After H, it will be I, and then it will be G, K, etc. But you have to remember only up to here. So I hope, yeah, that you can calculate the number of subshells in any shell. So can you now? It is easy. You have to remember the formula, that is subshell is given by the N formula, and N value, it is given by the L. L is always equal to 0 to N minus 1, correct? Shall I move to the next page?
Yes, sir.
Okay. Now tell me that this quantum number is also known as angular momentum quantum number. So that means this quantum number gives the angular momentum of an electron. So I will write it here that this quantum number gives angular momentum of an electron, right? Angular momentum of an electron. So how to calculate that angular momentum of an electron? That is, okay, I will write it here that angular momentum, it is actually known as orbital angular momentum, right? Orbital angular momentum, it is calculated by the formula that is under root of L into L plus 1 into h upon 2 pi, right? L into L plus 1 L into L plus 1 into h upon 2 pi. Got it? It is here L into L plus 1, right? You have to note down this. It is L into L plus 1, and then it is into h upon 2 pi, right? Got it? So can you tell me then what will be the angular momentum of an electron in, okay, you have to now remember this box. I will draw it here. This is very, very important. You have to note down this, that for S subshell, if we are having S subshell, then what is the value of L? S subshell, L value is 0. And for the P subshell, this table is very, very important because we will use it ahead a lot of times. So for P subshell, L value is 1. And for D subshell, what will be the L value? L value, it will be 2. We have actually seen it in the previous slide. You can just check it out there. For S subshell, L value is always equal to 3. So similarly, can you tell me what will be the for G subshell? For G subshell, what will be the L value? L value will be equal to 4. So it is just like this 0, 1, 2, 3, and 4. So you have to remember this L value for different types of subshells. Now, if I will just write a question here that calculate angular momentum of an electron, calculate angular momentum of an electron, calculate angular momentum of an electron in S subshell. So can you tell me the answer? Anybody? With this formula which I have given here, that is root of L into L plus 1 into H upon 2 pi. So what will be the angular momentum here? So angular momentum, if I represent angular momentum by AM, so angular momentum, it will be equal to root of square root of L value is what? For S subshell, what is L value? I told that this table is very, yeah, it is 0. So you will write here that is 0 into 0 plus 1 into H upon 2 pi. So that means 0 plus 1, that is 1. 1 into 0, that is 0. Root of 0, that is 0. 0 into H, 0. So that means everything, it will become 0. So this is very important, that the angular momentum of an electron in S subshell, it will be always equal to 0. So have you got it? This is very important. Sometimes question is asked that you have to calculate the angular momentum of an electron in different subshells. I have just told in case of S subshell. I hope that you can now calculate in P subshell, in D subshell, in F subshell. Can you? Isn't it? Have you noted down this? Shall I move to the next page?
Yes, sir.
Okay. So now let's see then how to calculate the angular momentum in case of P subshell. So can you calculate? Okay, just okay, I will write it here that calculate angular momentum of an electron, angular momentum of an electron in P subshell. In P subshell. So can you calculate the angular momentum in P subshell? What is the formula? Formula is that angular momentum, it is always equal to root of L into L plus 1, then it is H upon 2 pi, right? So what is the L value for P subshell? I hope you remember that table. For S, L value is
Yes.
0. Exactly. For P, it is 1. So I will just write it here. That is 1 into 1 plus 1 into H upon 2 pi, right? So what it will become? It will become C, 1 plus 1, that is 2. 2 into 1, that is 2. So it is the root of 2 into H upon 2 pi. Got it? So this is how to calculate the angular momentum of an electron in any subshell, right? So can you then tell me what will be the angular momentum of an electron in D subshell? So can you calculate this one? So it will be equal to, that is root of, what is the L value for D? For D, L value is 2. So that is 2 into 2 plus 1. Yeah, exactly. So 2 plus 1, that is 3. 3 2s are 6. So it is root of 6 into H upon 2 pi. Correct? Have you got it?
Yes, sir.
So Exactly. Okay, so shall I move to the next page?
Yes, sir.
Fine. So next, okay, let me first save these. So next we have to study the next quantum number. So what is the next quantum number? That is the magnetic quantum number, right? I hope you remember this magnetic quantum number. It is represented by small m. And this magnetic quantum number, it was given by the scientist known as Landy, Lande, Landy. So this magnetic quantum number, it gives the information about, okay, you will write down that it gives information about orbitals, right? First quantum number gives information about shells. Second quantum number gives information about subshells. And this quantum number gives information about orbitals, right? It gives information about orbitals, right? I have told you that what is an orbital. I told that it is the 3D space around the nucleus, right? Where the probability of finding an electron is maximum, correct? Okay, so this magnetic quantum number, its value, it is represented by m, right? And what it explains, this magnetic quantum number, it explains the splitting of spectral lines. So I will write it here. This is very important. If you remember that, I have told you that one of the limitation of Bohr's model was that Bohr's model could not explain the Zeeman and the Stark effect. That is the splitting of spectral lines, right, in presence of electric and magnetic field. So that is actually explained by this magnetic quantum number. So it explains splitting of, it explains the splitting of spectral lines. It explains the splitting of spectral lines in presence of electric or magnetic field. In presence of electric or magnetic field, right? So I will just write it here, that it gives the information about orbitals, and then I told that it explains the splitting of spectral lines in presence of electric or magnetic field. So you can just say that this magnetic quantum number, it gives orientation of an electron. It gives orientation of an electron. So that means whether electrons, they lie in the x-axis, whether they lie in the y-axis or in the z-axis. So that is actually the orientation. It gives orientation of an electron. This is very important. And how to calculate this m value? So you have to remember that this m value, magnetic quantum number, it's calculated as minus L through 0 to plus L. So this is the formula to calculate magnetic quantum number. I hope you will remember this because we have to apply this formula, magnetic quantum number. Magnetic quantum number. So it is represented by this small l, small m, and its value is calculated from L, azimuthal quantum number, that is minus L through 0 to plus L, correct? And I hope that you remember that table. I hope you remember that table. What I told? I told that for S, L value is 0, right? For P, L value is 1. I have already told this. I'm just repeating so that you will not forget this. For D, L value is 2. And for F, what I told, L value is 3, right? So can you tell me how many orbitals will be there in S subshell? So if I just talk of, for example, let's take the S subshell. So how many orbitals will be there in this S subshell? So for S subshell, what is L value? For S subshell, L value is 0, isn't it? For S, L value is 0. So therefore, what will be the m value? M value will be minus L, that is minus 0. Minus 0 is nothing. Actually, it will just come out here 0. Minus 0 through plus 0, through 0 to plus 0, that is nothing but the 0. But what here 0 actually means? 0 means one value. So that means there is one orbital. So in S subshell, there is one orbital, and that orbital is known as S orbital. So that means the name of subshells and the name of orbitals, it is same. So one orbital, you will just write that this orbital is known as S orbital. So the name of orbitals, it is same as the name of subshells. So have you got it? Have you noted down this? This is very important, that in the first, that is your S subshell, since L value is 0, therefore M will also be 0. So 0 doesn't mean nothing. 0 means one value. 0 is one value, right? So it means one orbital is there, and that orbital is known as S orbital, right? Have you noted down? Shall I move to the next page?
Yes.
Yes, sir.
Okay, so then let's see the P subshell. So in P subshell, can you tell me how many orbitals will be there? In case of P subshell. In P subshell, we know that what is the L value? L value is 1. So what will be the M value? Therefore, M value is, we know the formula, it's minus L through 0 to plus L, right? Okay, now what is here? Minus L value is 1. So minus 1, then it is through 0, and then it is plus 1, plus L. So that's plus 1. So how many values we are having? We are having 3 values. So that means there are 3 orbitals. Correct? Have you got this? So in case of P subshell, there are 3 orbitals, and these 3 p orbital, these 3 orbitals, they are known as p orbitals. Correct? They are known as p orbitals. So p orbitals. Now, what is the actual name of these 3 p orbitals? There are 3 p orbitals. One is known as px, another is known as py, another is known as pz. So here it is very important to note down that for this pz, m value is taken as 0. For pz, you have to remember that m value is taken as 0, because there are 3 values. One is minus 1, another is 0, another is plus 1. But 0 is always for this pz. You have to remember this, that for pz, m value is taken as 0. And then it is px, py. So they can have plus 1, minus 1. So px and py, they can have any value, that is either plus 1 or they can have minus 1. But 0 is always fixed for this pz. This is very important. I hope you will remember this, that for pz, m is taken as 0. Got it? Have you noted down this?
Yes, sir.
Okay, then tell me, in case of D subshell, how many orbitals will be there in case of D subshell? What is the L value for D? It is 2. Okay, therefore, can you tell me the M value? M value will be minus L, so that is minus 2. Then it is through 0, and then it is through plus 2, correct? So that means it will be now minus 2, and after minus 2, it is minus 1, and then it is 0. After 0, it is plus 1, and then it is your plus 2. So how many values we are having? In total, how many values we are having? We are having 5 values, 1, 2, 3, 4, 5, right? So that means we are having 5 d orbitals. So in case of D subshell, there are 5 d orbitals, right? There are 5 d orbitals. So can you name these d orbitals? They are very important. So they are named like this. One is known as dxy, another is known as dyz, another is known as dzx, another is known as dx square dash y square, another is known as dz square. So these are the 5 d orbitals which you have to remember here. So that means in case of d subshell, there are 5 d orbitals. One is dxy, another is dyz, another is dzx, another is dx square dash y square, another is dz square. Correct? Now, can you tell me here that this zero value, it will be for which d orbital? This zero value will be for which d orbital? Can anybody tell me? Just as I told that this zero in case of p, this zero, it is for this pz, right? Similarly, you have to note down that here in these 5 d orbitals, this zero value, it is for dz square. So you have to remember, okay, I will write it here that for dz square, m value is always taken as 0. Got it? Shall I move to the next page?
Yes, sir.
Okay, so now I hope that you can calculate for f subshell yourself. Can you calculate for f subshell? F subshell. For f subshell, what is the L value? L value is 3, right? Therefore, what will be the M value? Magnetic quantum number, it is minus L, that is minus 3. Then it is through 0. And then it is up to plus 3, that is plus L. So minus 3, then it will be minus 2, right? Then it will be minus 1, then it will be 0. Then it will be plus 1, then it will be plus 2. Then it will be plus 3. Got it? Have you got it?
Yes, sir.
Yes, very important. Now tell me here that how many f orbitals we are having in total? So that means I am having 1, 2, 3, 4, 5, 6, 7. So there are 7 f orbitals. 7 f orbitals. So I will just write the name of these 7 f orbitals. If you can remember, that is good. But if you cannot remember, it's also good. So one is your f x cube, another is f y cube, another is f z cube, another is f x y z, another is f x y square dash z square, another is f y z square dash x square, and the last one will be f z x square dash y square. So these are your 7 f orbitals. Got it? So now if I just tell you that this 0 value, it will be for which f orbital? Can anybody tell me this 0 value? This 0 value will be for which f orbital? If you have just noted from P and D, then you can easily tell. So can anybody tell me this 0 will be for which f orbital among these 7? It will be definitely for this fz cube, right? For fz cube, okay, I will write it here, that for f z cube, m value is taken as 0. Got it? So that means this magnetic quantum number, it gives the information about the orbitals, and we can just calculate the number of orbitals just as we have calculated in case of s subshell, p subshell, d subshell, and f subshell. And next will be the homework for you, that you have to calculate the number of orbitals in case of g subshell. Can you calculate? Calculate number of orbitals in G subshell. So can anybody tell me how many will be there? Can you calculate the number of orbitals in G subshell? Have you noted down this?
Yes, sir.
Okay, so let's then, this will be the homework. I hope you can easily calculate this one. That is the number of orbitals in G subshell. Let's revise what we have studied, right? Let's recap. So we have just started from the wave mechanical model, right? So can you just turn your camera on so that I can interact with you? We have just started from the quantum mechanical model or the wave mechanical model, right? There I told that with the help of this wave mechanical model, we actually got the concept of orbital. And orbital is nothing but the 3D space around the nucleus where the probability of finding an electron is maximum. Maximum means 90 to 95%. And this orbital, it is 3D. It follows the Heisenberg's uncertainty principle. And then I told that there are different orbitals, S, P, D, F orbital, and different have different shapes. S orbital is spherical, P orbital is dumbbell, D orbital is double dumbbell, F orbital has complex shape. And then I differentiated between the orbit and the orbital. I hope that you can go through that and you can remember that the maximum number of electrons which can be accommodated in an orbital, that is always 2, right? This is very important. And the maximum number of electrons that can be accommodated in any orbit, that is given by 2n square. For example, in case of K shell, there are 2 electrons. In case of L, there will be 8 electrons. In case of M, there will be 18, then 32 electrons in case of N shell. Then I just told you the postulates of this quantum mechanical model. And there I told that the first postulate is that the energy of an electron, it remains always quantized. That means it has fixed values. And those quantized values of energy, they are actually obtained from. And then I told you that it is impossible. What is impossible? That is to measure the exact position and the momentum of an electron with absolute accuracy, correct? And then I told you that atomic orbital, it is described by the wave function psi, and since psi has different values, so therefore there are different orbitals like S, P, D, and F. And then I told that this psi square, it gives the probability of finding an electron around the nucleus in 3D space, right? So more the psi square, more will be the electron density, that is the probability density. And then we just move towards the quantum numbers. I told that the first 3 quantum numbers, that is the principal, the magnetic, and the azimuthal quantum number, they are just obtained from the solution of Schrodinger wave equation, the first 3 quantum numbers. Then we discussed the first quantum number, that is the principal quantum. And what are these quantum numbers? They are simply the set of 4 numbers which give the complete information about the electron in an atom, right? And then I told you that this first quantum number, that is principal quantum number, it is represented by small n. It gives the information about shells, right? And the second quantum number, it is represented by small l, that gives the information about subshells. And then the third quantum number, magnetic quantum number, that's represented by small m, that gives the information about orbitals. I hope you will remember those formulas in order to calculate the number of subshells, number of orbitals, and the different names of the orbitals, correct? So are you having any doubt, any question, any query in today's class? You can let me know.
No doubt.
No, sir.
Okay, then have a nice day ahead. Thank you.
Thank you, sir.
Have a good day ahead. Okay,
Thank you, sir.
most welcome.